Torque review. Let's begin. So how do we define torque? Well, um, this is a force that causes an object to rotate about a pivot. All right, so two important things here. You got a pivot and you got an object rotating. All right, so basically, a good example of this is an upwards view of a door. All right, so let's say I'm imagining you're looking at the door from above it. And I know there's a formal word for that, but I can't really recall what the word is. And this is the hinges. The hinges are the pivot. All right. Now, there are a few factors. There are three factors that contribute to how large a torque is. All right. The first factor, all right, let's see, factors that contribute to large torque. Yeah, the first factor, we got magnitude of force. All right. Second one, distance of a distance from pivot to point of force application. All right, so like it's my pivot, and I have a force acting over here. The force with a larger R is going to be larger. And the last one is the angle at which force is applied. All right, so yeah, and our formula for torque is at least the magnitude of torque. The magnitude of torque is F so and times R, where R is the distance from pivot to force application. The force applied zone. And then F is the magnitude of the force applied. Okay, so basically what we're gonna talk about here is this door example. Yeah, sorry, I kind of blanked there for a minute. This door example. What forces here? We've got F1, F2, F3, F1, F5. What force here is the most positive, so to say, at least the largest in positive magnitude. Or let me actually just make it simple. What forces here will have the highest effect in rotating the door? It's F1. All right, if you recall, it's F1. Why? Because F1 is perpendicular to the radius, the radial line. All right. Our R points from the pivot. Let me change my color. Points from the pivot to, it's supposed to be a straight line, to the point of force application. All right. Okay, it's not straight, but I hope you get the point. So this is my R. So I have a large R, and I'm directly perpendicular to the radius, to the radial line. Sorry, we call that the radial line, right? F3 is perpendicular, And in fact, you would say they're both equal in magnitude, that they both rotate the door in equal strength. But the fact that F1, when you rotate it using F1, it goes in the counterclockwise direction. So remember, counterclockwise, counterclockwise is positive, and then F3 takes it clockwise, so it's going to be negative. F2 will have a perpendicular component as well, but that depends on how large F2 is for it to really be effective, more effective than F1. F5 here has a very small r, so because our formula is torque equals force times distance from pivot, we can clearly see that F1 will have even F3 with a larger magnitude of force, of torque than the rest. Then F4 won't even open the door because the force is parallel to the radial line, all right, to R. The force is parallel to R. So the forces that are parallel to the pivot, or to the radial line, all right, forces that are parallel cause no torque. All right, forces that are parallel cause no torque. All right, so let's look at the door example closely. All right, I already gave you a formula in the previous section for torque. So we know torque is F, actually the perpendicular component of F times R, as well as you could use this. You got the magnitude of the force times the perpendicular component of the radial line. Also, this is also known as the lever arm or the moment arm. And then this is the magnitude of force. All right. So let me help you visualize what F perpendicular is. Yeah. So F perpendicular is the perpendicular component of F2. So if I want that component, this right here is F perpendicular, and this right here is F parallel. Remember, yesterday in the previous section, we saw that F parallel, or should I say forces that are parallel, exert zero torque. So to find this, in finding this, I know that I can just easily decompose this vector, my cos theta and my sine theta. Like cos is opposite of hypotenuse. Sine is nope, that's sine, that's not cos. Cos is adjacent over hypotenuse. That's cosine. Let me redo this nicely. Okay, so now if I get my opposite, let me do my sine function. If I get my opposite, sine theta, it's going to be equal to, let's say opposite, the angle is going to be F perpendicular over the hypotenuse F2, and F perpendicular is going to be equal to, if I cross multiply, F2 times sine theta. All right, so we can see to calculate our torque, we have to multiply F2 times sine theta times R. All right, good. So that's one way to find the torque, just getting the perpendicular component of the force. It won't always be sine theta. It's always good to just go through the whole derivation, because sometimes it's cos theta, and if you get those mixed up, your answer could end up being wrong. So now let's try to use the moment arm. So the moment arm is basically obtained by a two-step process. The first step is you need to get the line of action. The line of action is just a straight line that goes along the force vector that's been that aligns with the force vector. All right. So you see, my force applied was F2 on this door, and I have a straight line just going through that. So that's my line of action. Then I connect my pivot to the line of action, and that forms a 90-degree angle. And I have another right angle triangle, right? And through geometry, here I have a foot triangle because this my R is still existent here. R. And then this right here is called the moment arm. All right, this is the moment arm, or if you like, the lever arm. So first you draw your line of action, and then you draw a line perpendicular from your pivot to the line of action. That's your moment arm. And then how would you get this moment arm value? Well, geometry tells us this is theta. If I get my cosines and sines, I believe it's a sine. This one's sine. I know I'm guessing, but we'll see. Up over hypotenuse. So my sine theta is going to be equal to my opposite. It's going to be r perpendicular over r. All right, over r. So I cross multiply. I know r perpendicular is going to be equal to r sine theta. So from there, my torque is going to be equal to F, and if my force applied is 2, I just plug in the perpendicular component, r sine theta. We can see that these two are equal. All right, these two are equal. Even though they're in different places, when you multiply, you can just do whatever you want in some way. But yeah, these two are equal. And sorry, when you multiply, it doesn't care where your elements are, how they are arranged. Because whether you multiply in this arrangement, it's still gonna be equal. So now, why would you use one over the other? It depends on the situation. Some situations you will see your moment arm is very easy to attain, so use your moment arm. Some other situations you'll see your perpendicular component is easier to attain, so you use your perpendicular component. But either way, they are both very true methods. You can use them for any situation. Just that sometimes one will be more complex than the other. And net torque. All right, net torque. Remember, this is really important. So what we saw, the factors that contribute to a large torque, a force, radius, well, that's really important. But the net torque on a system is really just the sum of all the torques acting on a system. All right. So if I have 3 forces acting on my system here, yeah, and they're causing it to rotate about this pivot. Remember, the rotation about the pivot is very important for torque. All right. I know they all have a distance r from the pivot, r1, r2, r3. So if I want to calculate the net torque, it would be very useful for a dynamic equation. So I know I have torque 1 plus torque 2 plus torque 3. So I know the formula for torque is going to be RF. So torque 1, I know is R1 F1 plus torque 2 will be R2 F2 plus torque 3 will be R3 F3. All right, and they can be as many torques as they can be. And notice these are all positive, and the reason they're all positive is because they rotate the system in a counterclockwise direction. But if one of the torques, let's say for example we had a torque here, it pointed downwards, yeah. Let's say this is R4, F4, it would have a negative sign. So hang on, we have a negative sign, and it's going to be minus. It's going to be minus, because you see this is pointing downwards, so it's going to rotate the system counterclockwise. Minus F4 R4, or rather, let me put this nicely, R4 F4. All right, and that was really it. A relatively short video, just reminding you guys the nitty-gritties of torque. I hope you guys had a good break, and yeah, I can't wait to see you guys. Ciao.